High-velocity free surface flows often occur on open-channel conveyance structures such as spillways. These flows are characterized by aeration, a process where air enters a body of water and produces complex three-dimensional flow structures and intense motions at the air-water interface. The air incorporated into the flow falls under one of two categories. There is the air transported as bubbles, referred to as entrained air, and air which is transported within waves of the water surface, referred to as entrapped air. Under these conditions, the average air distribution within the air-water column, referred to as the time average void fraction distribution, is arguably the most important parameter to inform engineering design. Currently, we can only resolve the void fraction distribution through the instrumentation of phase detection probes. While these probes perform very reliably under controlled flow conditions, such as those on a laboratory scale physical model, their intrusive nature means they cannot measure much larger flows, such as those on a full-scale prototype structure. The current inability to collect prototype data means that despite being a critical part of the engineering process, none of the approaches that engineers routinely use to estimate void fractions of the flows that they're designing for can receive definitive validation. This is the fundamental problem that plagues hydraulics engineering and the driver for much of the current research, including my thesis. The solution lies in an instrument that has the following two attributes. It has to be non-intrusive so that it can mitigate the limitation that has prevented phase detection probes from prototype scale applications, and it has to measure data that can resolve the void fraction. Naturally, instruments that operate based on remote sensing have been featured in many studies so far, as they all satisfy the first requirement of being non-intrusive. Following the current research trajectory, I investigated remote sensing instruments in the form of LIDAR cameras in the Intel L515 and Apple iPad. These consumer-grade LIDAR cameras have only recently become available to the mass market, and my thesis is the first to assess their potential in hydraulic engineering applications. I performed all my experiments on a laboratory-scale spillway model at the WRL. I recorded observations of various flow rates with the LIDAR cameras measuring from the top view. To gather ground truth against which I could compare the results, I performed simultaneous experiments with a phase detection probe. What you're looking at right now is one of the recordings from the L515, with the measured points expressed in terms of their elevation from the channel bed. This is the first time temporal and spatial variations have been captured in such high levels of detail. In the video, you can clearly see what appears to be splashing and waves propagating along the channel. Now, even though the video is very interesting, what I wanted to investigate is whether the data can be linked to the time average void fractions from the phase detection probe. What I wanted was for the average elevation from the data to follow the same profile as the void fractions, which is relatively uniform. Unfortunately, this is what I found instead. For the L515, the average elevation of the flow rates that I investigated always had this characteristic bulge in the region right underneath the instrument. The elevations are also very low, even lower than the elevation at which the void fraction is only 10%. This is very unexpected, as you would think that the signals are bouncing off somewhere near the surface. Instead, it appears that most signals actually penetrate much deeper into the flow. From these results, it seems that the L515 is not suited for this type of application. Moving on to the results of the Apple iPad. The average elevations appear much more reasonable. They are higher up, around the elevation where the void fraction is 70%. However, the profile is still inconsistent with the void fraction profile. They are also inconsistent with each other, with some trending downwards and others upwards. So, even though my results indicate that neither cameras have potential in hydraulic engineering applications, it is important to keep in mind that this is the first time LiDAR cameras have been studied. There are things I know now about how these two particular devices function that, had I known sooner, would have improved my methodology. As you can imagine, neither of these devices were intended for use in research, but the Apple iPad in particular really restricted my ability to acquire and process data in a rigorous and systematic way. For now, the potential of LiDAR cameras is inconclusive, and the results of my thesis require further verification with more robust data acquisition and post-processing procedures.